Good morning, everyone. I am Pooja Dabhal, Marketing Coordinator at Cengrs, and the moderator for today's highly anticipated webinar on Introduction. Welcome to the sixth edition of Cengrs webinar series. Today, we'll explore the fundamentals of cone penetration testing and its application to geotechnical investigation. I'm honored to introduce our speaker, Mr. Sorabh Gupta, Director of Cengrs, who brings over 20 years of experience in the geotechnical engineering industry. Before we begin, I'll pop your comments and the questions in the chat box, and we'll address them live during the session. So please do share your thoughts. Over to you, sir.
Thank you very much for organizing this puja, and very good morning to everyone in the audience. We've done this webinar once before. There were a lot of requests, private requests to repeat the webinars. So on that basis, we have decided to use this beautiful Saturday to once again go through this presentation. The intention of this webinar is to introduce cone penetration testing, or CPT, to the wider audience. CPT testing, as we'll find, is not new. It is a very old and a very well-established technology worldwide. In India, I think we are still in the adoption phase, and at Cengrs, we are trying hard to make these new advanced investigation tools more popular and bring them into the mainstream. So, without much ado, let's start. I'm Sorabh Gupta. I'm director at Cengrs Geotechnica Pvt Limited. We are a New Delhi-based geotechnical consultancy company. And the topic of today's presentation is Introduction to Cone Penetration Testing. Very quickly, Cengrs is one of the older and more reputed geotechnical engineering consultancies in the country. We are now 34 years young. The company was established in 1990. We have a small team of around 160 people, and we have completed over 6,900 projects across the Indian subcontinent in these last couple of years. We like to believe we have one of the larger private geotechnical data banks in India, and this is something we are very proud of. Also, on the aside, we do have obviously NABL accreditation. While we were one of the first companies to get NABL accreditation for our laboratory, so around 20 years back, we have now extended our scope of accreditation to cover the full range of field tests as well. And this is something which we encourage all geotechnical engineering companies to do, just to improve the quality of our services. In terms of what we do is essentially everything to do with soil and foundations, primarily geotechnical investigations, geophysical investigations. Also, we support this activity with lab testing, consultancy jobs, foundation testing, and a little bit of topo and hydrological services. We do believe in 360-degree solutions. So, and I think this is critical. Very often in a project life cycle, these three hats are worn by different people, and that causes avoidable complication in the project. So what we believe is we offer not only geotechnical investigation services, we also follow it up with consultancy or foundation design works. And finally, we like to bring that design or realize that design on the ground by offering foundation QA/QC services as well. Because end of the day, no matter what you do on paper, if you can't achieve it on site, then there's absolutely no point. So it's a 360-degree solution. So the 1 point responsibility for your foundations. In terms of markets that we serve, I mean, foundations, geotech investigations are required for pretty much any kind of project. And so we are lucky that we get to work with a wide array of projects, a wide array of customers. We are very big on the energy sector, where we have done possibly investigations at 70 to 80% of the power plants in the country. We also work in nuclear, wind, solar. We have done a lot of high-rise building works. Lately, this is coming back into fashion. So we are doing I think around 26 high-rise building projects right now. A lot of work on bridges, highways, metros, industrial, water supply, and so on and so forth. For the geotechnical investigations and the themes which we are speaking about are going to be common irrespective of what you're building. The concepts remain the same. Cengrs as a company was started by Mr. Sanjay Gupta, Mr. Ravi Sundaram, and supported by me and the latest entrant. So three of us are the technical leads, of course, supported by a large team of geotechnical engineers and other support staff. This is what we are proud of. So 6,900 projects across the Indian subcontinent completed over the last 34 years. And we have very nicely organized this data bank in-house as well. That is very helpful for us to understand the stratigraphy in any location based on past experience. With that, let's jump into what is good geotechnics. I always put a couple of slides for this in every presentation. We always say that there is, in many conversations, people will talk about, site kharab hai and soil kharab hai, the ground is difficult. We do believe that there is no such thing as difficult ground, just like a Rubik's Cube. It's difficult only if you don't know how to work with the ground, if you don't understand the techniques, if you don't have the knowledge and the experience. But if you have it, then, it's quite straightforward. At the same time, and I find this cartoon very useful, it's also not simple. Right? Geotechnical, and I think we fail to appreciate how difficult geotechnical investigation is. End of the day, we are poking a few holes in the ground, and we are trying to work with a material which is fairly complex as compared to steel and concrete and other man-made structures. Materials, geotechnical is fairly complex. We do have a range of simplifications, oversimplifications, which we use to come up with our interpretations. And that requires a lot of experience, and it requires a little bit of art. We do believe also that site characterization or soil investigation is not a one-shot job, and I think this is the key. Is every time you have a project, you must never do your ground investigations based on a copy-paste job. All the stakeholders must sit across the table and work out the optimum scope and extent of the site characterization program, and that's very important to avoid unforeseen circumstances, to mitigate risk, and also for a little bit of value engineering on that project. We have introduced these levels lately, and we like to say that you can, depending on your site and ground complexity, you can carry out investigations ranging from bronze to silver to gold to platinum level, and we'll see what they are. But essentially, this is different levels of geotechnical input, and we always like to tell our customers that in the end, you will get what you pay for. So if you must look at investigations as not an expense on the project, but rather as an investment into your project. And really, this will you'll always get your return on investment by doing so. I'm not going to go into the details, but primarily, the concept is, bronze level of investigations is if you have, say, a simple structure in a geology which is fairly well known, fairly competent, then maybe you can get away by doing just, say, a few shallow boreholes, a little bit of conventional testing, and some simple design. So that's bronze level on one end, and obviously this is the cost of investigation is cheaper, but there is a fair amount of conservatism which is built into the analysis, which might be acceptable for a simple project. On the other end of the spectrum, if you're looking at a tall building, with high loads, possibly in an area where you have, ground conditions which are not very competent, we may want to go with several stages of investigation. We may have to go with some level of site-specific or in-situ investigations, some advanced lab testing, some advanced analysis. And whereas while the cost of such a platinum investigation might be slightly higher as compared to bronze investigation, what you'll find essentially is that you get benefit in terms of reduced cost of foundation. So this is a plot from the NCHRP survey, where you see that as your cost of site investigation increases on the x-axis, increases as a percentage of your project cost, there is some reduction in your foundation cost on that project. With that, let us talk about in-situ testing. This is essentially what we're trying to do in geotechnics. Is, we are trying to put our head into the ground and figure out what's going on underneath. It's really not easy to do this. It's quite tough, but we manage. I'm going to jump this, and I'm going to talk about this very often, and primarily in India and many other developing countries. When we talk about geotech investigations, we think that we are talking about boreholes, right? And it's almost become synonymous that that geotechnical soil investigation is the same as borehole drilling, and we are trying to change that mindset, and it's very important. GTI is not only about boreholes. If you really look at why, there are a lot of limitations to borehole-based investigations. First of all, the gold standard of investigation these days, or still unfortunately, is SPT, the standard penetration test. So we always like to educate our customers that there is nothing standard about the SPT. The SPT value depends on many things, including the drilling and borehole technique, the SPT equipment used, the test procedure, energy delivered, overburden pressure, the ground conditions, and so on and so forth. So the SPT value, which we hold in such high regard, you have to be very careful before you use it. There are a lot of sources of error. There are a lot of variability in the SPT values, which might affect your final outcome and your geotechnical analysis. Aside from SPT, when you look at lab testing, there are obvious limitations, well-known limitations in sampling, in sample transport, in lab testing, as well as in the empirical design methods that we use. So I think if you look at the picture on the right, you see how we are trying to interpret directly, indirectly, so many parameters based on very little information that we get from borehole investigations. And that is something, this thinking that GTI or geotechnical investigations is all about boreholes, this is something we are really trying to change. I think the time has come in our country also today to bring about a paradigm change in the way we look at investigations and understand that investigations is not just boreholes. There's a lot of options. So, and I always like to say, just like, a gardener has got various tools which he uses for various purposes. You can't just go with a hammer and, do all your work with it. Same way, SPT is great, but it does not apply in all circumstances. It's not as useful in all circumstances. As geotechnical engineers, we also have a wide array of tools which are available at our disposal. Some engineers might find this surprising, but if you look at this graph, and I love this plot, this is by Professor Main, you'll see how many tools we have at our disposal, and we must learn to pick and choose the right tools for our site depending on the application, depending on the ground conditions. Quick summary of the various in-situ tests and their uses. If you look at static analysis on the left-hand side, so SPT, of course, is very well known. Field wind shear test is very useful for characterization of soft clays, like in Kochi and other coastal parts of India. CPT, piezo cone, seismic cone, we are going to talk about it today. The alitometer is almost not very popular in India, except in research. Pressure meters are catching up, very useful again for determination of in-situ modulus profile, and so on and so forth. Dynamic analysis also, we have a lot of options, which is on the right. Some of these are fairly common now, like seismic refraction testing, cross-hole seismic testing, MASW to some extent, and while other techniques are still catching up. This is another good plot by Professor Robertson. It's in his book. And you see how different in-situ tests each of them have their own strengths and weaknesses. And we have to understand this sort of like SWOT analysis of different in-situ test methods because you have to understand, depending on what geotechnical parameter we are trying to obtain, or depending on what is the ground type that we are working in, we have to be able to go back and really think and pick our in-situ test method depending on what we want. So it's kind of a case of one shoe does not fit all feet, right? So if you are looking for example, since we're talking about CPT today, if you see CPT, and A means that there is very high applicability. So if I'm working in CPT, has got very high applicability in pretty much all kinds of formations except for maybe gravel. And if you look at what in terms of geotechnical parameter, so CPT is got very high applicability for determination of soil type, for soil profiling, for determination of pore pressures, and so on and so forth. You see most of the parameters are A and B, right? So it's a very robust test, and you compare that with SPT. SPT actually surprisingly has got fairly low applicability for most of the geotechnical parameters. We now come back to the topic of today's presentation, which is CPT. I'll just dial down and talk about first the test equipment. So let's look at this, starting with the cones and the CPT samples. A little bit of history. I mentioned earlier that CPT is not a new technique. So it's actually not new at all. It goes back all the way back to 1932 when the Dutch invented the mechanical cone, which has been used for quite some time. The early Dutch mechanical cone, 1932. A couple of years later, Delft came up with the Dutch mechanical cone, and this is what in India till date we have been calling, the SCPT, or the static cone penetration test. Usually we were referring to this kind of a mechanical cone apparatus. Couple of years later, someone came up with the Fugro rather came up with the electric cone, and in 1974 the piezo cone was invented. Now notice it's been 50 years exactly since the piezo cone has been in use internationally. I mean, I remember when I started my career in the States 20 years ago, CPT was the way to go. There were very few boreholes being done. And 20 years later in India today, we are still introducing CPT for the mainstream investigations. So a lot of catching up for us to do. The good news is definitely the BIS codes, or the Bureau of Indian Standard, BIS codes have caught up. In 2021, the main code for geotechnical site investigations, which is IS 1892/2021, actually introduced the piezo cone test method, and you see a snapshot here in the code. So that is the first time. I'm happy to announce also that there is a committee which is in place. I'm a member of that committee, where we are trying to also come up with a standalone code for CPTs, for electric cone and piezo cone testing. And hopefully this code should come out. It's in draft right now. It should come out hopefully later this year. So fingers crossed for that. I want to talk about nomenclature because this is often there is a lot of confusion for this. DCPT is dynamic cone penetration test. This is a very simple, very old technique where you take usually a simple cone, it's non-instrumented, this mild steel cone, and you kind of just hammer it into the ground, and you see number of blows per foot. The SCPT in India, when we say SCPT, typically we are referring to the mechanical cone. MCPT is the same as is really the mechanical cone. This is the internationally adopted nomenclature. So normally we for mechanical cone, MCPT. When you use an electric cone, where it's referred to as eCPT or simply CPT. If you look at the ISO code, it calls it TE1. You add some pore pressure measurements to the electric cone, and you get eCPTU. So U standing for pore pressure, or simply CPTU, or some people call it PCPT for piezo cone penetration test. If you look at the ISO code, calls it DE2. And when you add seismics to the same cone, usually you'll call it SCPT, not to be confused with SCPT in India, which is mechanical cone, but SCPT for seismic cone penetration test. To be clear, we also refer to it as SCPTU, which is seismic cone with pore pressure measurements. So I think the what you see in bold, so MCPT, ECPT, CPTU, and SCPTU, that is what we are preferring to use for for Indian context. I'm going to jump this. We will speak more about this as we move forward. But again, these are just the acronyms and what kind of measurements we are taking. So mechanical cone, electric cone, piezo cone, and so on and so forth. If you look at the cones, once again, if you look at the cone, so this is on the left, you see the electric cone, the piezo cone. This is a good slide because it highlights how, in the electric cone, you are measuring the cone tip resistance and the sleeve friction, whereas in the piezo cone, you are basically adding the pore water pressure measurements. So U2, which is right behind the cone. And the cones are different sizes also. So we'll talk about this. The cross-section area, typically 10 to 15 square centimeter, the typical cone sizes. Of course, there are other cone sizes also, but the 10 square centimeter and the 15 square centimeter cone size is fairly standard. A little bit of history now. This is a mechanical cone, or the SCPT. I don't want to call it, so it's MCPT for the mechanical cone. So this was a fairly simple setup. This was a mechanical cone pushed with a hydraulic pusher. And in this kind of setup, actually, the measurements were not made at the cone level. So we used to really just, there were pressure gauges on top of the pusher, and we used to measure the pressure in the hydraulic oil, which was used to push the cone down. So the measurements were made at the ground level. And it's a very simple setup, because there was no sensors at the cone tip level. So it is an indirect measurement, so to speak. We used to get, the readings from the guy used to stand, and we used to read the pressure gauge, as it used to fluctuate very quickly. We had to pick up, the pressure values as the cone was pushed down. And then we used to pick up those pressure values, multiply by the area of the hydraulic jacks, and we used to get the load. We used to plot this in Excel and get the resistance profile. So not a bad test, but at that time, of course, a very innovative test method, but it had several limitations in terms of accuracy. The measurements were made. We ultimately were measuring pressure, so there was an issue with accuracy. While the cone tip values were fairly okay and usable, the friction values really were not very usable. So you couldn't really use the mechanical cone data for stratigraphy. You could only use it to get maybe some idea of the cone tip resistance profile with depth. So we did upgrade. So we moved on to piezo cone now, and so this is on the top left. This is what a piezo cone looks like. Different probe sizes. I mentioned earlier that the cones are different sizes. Now look at this. So you actually have a 2 square centimeter and a 40 square centimeter cone as well. Not very common, definitely absent in India today. But the 2 square centimeter cone has the advantage that it can be used where you have soft clays in offshore conditions, because you require very little thrust to push it in, and also it has higher sensitivity. On the other end, a larger cone like the 40 square centimeter cone is useful for gravel soils. Coming back to the piezo cone, this is the piezo cone. You have a bunch of transducers in the piezo cone. So you have pressure transducers. So this is how the cone is constructed. So you have transducers at the cone tip level, where you pick up the cone tip resistance. You have transducers, the strain gauges along the sleeve, where you can pick up the sleeve friction. You also have an inclinometer at the top, which will give you the inclination of the CPT apparatus. If you have a seismic cone, you have geophones. If you have a piezo cone, then you will also have some transducers at just behind the cone to measure the dynamic pore pressure values as well. On the right, you will see how you have a pusher, and the rods and the cone is pushed into the ground. And I always appreciate how a single push is giving us so much data. So we are actually measuring, I want to clarify this, we are measuring depth of the cone, because there's a depth encoder which is attached with the equipment. So we are measuring depth electronically. We are measuring the inclination. We are measuring cone tip resistance. we are measuring slip friction, and we are measuring dynamic cone pressure, dynamic pore pressures. So these 5 measurements are what we get, and we get continuous readings as the cone is pushed down. Little bit of table. I'm not going to go through this too much, but if you look at a piezo cone versus mechanical cone, world of a difference, in my opinion, in terms of test data resolution. Obviously, piezo cone being electronic has got much better data resolution, actually 20 times better, much more repeatable, and you have the advantage in the piezo cone that you can measure the pore pressures, which is something we obviously could not do in the mechanical cone. We can measure the cone inclination, which becomes quite important as well, and we'll see that. And the QC measurement in the piezo cone is quite representative of all kinds of soil materials and very useful for getting the soil behavior type values as well. There are other advantages. For example, in the piezo cone, we can stop the cone and we can do a dissipation test. We will see that a bit later in the presentation. Report preparation, because all the data is electronic now, so there is no manual intervention at any point of time. So the data collection, data transfer, as well as the data interpretation are all done at the click of a button. So the report preparation also, you kind of just import the data into a software, and the software will spit out the analysis and the report, including the foundation analysis based on CPT. And that's great, right? Because that actually takes away a lot of human errors in the processing of CPT data, and that's very useful. We will talk about seismic cone later. It's essentially the same as a piezo cone, except you have a couple of geophones which are included with the cone setup. So now you can actually stop the cone and you can do some seismic testing as well. A lot of people, initially when we were talking about CPTs a couple of years back, when we introduced CPTs in India, a lot of people, pushed back saying that, hey, CPT is great, but we don't get samples, and we need samples. We need to see the sample, and we need to do some lab testing. And I think I never understood why that's so critical, because you do have a few boreholes on the same site. But in spite of that, we did import a few CPT samplers, and this is so the push is that even in a CPT profile, it is possible, if you really want, it's possible to stop the cone and put a CPT sampler and pick up some undisturbed samples at discrete depths. The added advantage over regular boreholes is, in boreholes, you are kind of just picking up samples at regular depths, right? In CPT, because you are actually getting continuous profiling, and you can see the ground resistance and this ground type changing while you're doing the testing, the added advantage is that you can actually do a CPT push. You can understand where is the silt, where is the clay, where are the loose pockets, so on and so forth. And you can shift the apparatus maybe a couple of feet aside, and then you can push again, and you can actually design particular depths at which you want to take your undisturbed samples. So I want to mention this because this is great. Rather than arbitrarily, collecting samples in all kinds of strata, we are trying to collect undisturbed samples in sand, in clay, and so on and so forth. Here, you can actually look at where are the clay layers, and you can go down to that layer exactly, pick up an undisturbed sample from the clay layer, and take it to the lab for testing. So that's with the cones and the CPT sampler. Let's take a quick look at various pushers and testing procedures as well. This is essentially what a CPT test looks like from the ground surface. Is you have any kind of pusher, you have a bunch of push rods, and these are hollow rods because the cables need to run through the rods. And then you have the cone or the penetrometer, which is pushed into the ground. So there is no need for boreholes. You simply have a cone, you put it on top on the ground, and you push it down until you meet refusal, essentially. So various kinds of pusher arrangements. You can use a Kentledge or a deadweight kind of system because it doesn't matter. See, the intention of the pusher is eventually you are just trying to give the cone a reaction system, right? So it doesn't matter what is the shape and nature of your pusher. So a deadweight system works well if you have to. Otherwise, what we prefer on most sites is we use anchored trailer-mounted pushers. So these are fairly simple. These are nice, lightweight pushers, 20-ton capacity. And we actually use, apart from the weight of the pusher itself, we use a couple of earth augers. Here on the top left, I'm sorry, I don't have a pointer here, but on the top left, you can see how we installed a couple of augers, earth augers. So you can install, say, 4 to 8 earth augers, and this will give you enough reaction to push the cone down. So very nice, small equipment. It can reach many kind of locations, so easy accessibility, easy transport. So that's the anchored. CPT trucks are very popular in North America. So the advantage of this is a ballasted system. So there are no augers. The truck itself, weighs 20 tons or more actually, and the center of gravity of the entire pusher system will be roughly where the cone is situated, and the cone is situated inside the truck. So a very nice system where the team can kind of get into a truck, drive to the CPT location, and they have the container at the back, so they can sit in the container, do the test. All the electronics are safe inside the container as well. We also have crawler mounted, so in case you have difficult site conditions or the access is a little tricky on site, the truck can be modified into a crawler kind of system, so you can crawl to various locations. And then, if you look at a couple of photographs, people have come up with all kinds of pushers depending on their use case. In fact, these days you also have what is known as a track truck. So this is a combination of the track and the truck system. So the trucking is good for long distance shifting, and whenever you want to move in a difficult terrain, the track just comes down, lifts the tires up, and then you can track or crawl from one location to the other. So very nifty. I think a lot of innovation has been from Europe and North America. Manufacturing in India is still awaited, and hopefully we will be manufacturing CPT rigs in India soon. Again, for special situations, look at this. So you have for small, for if you don't have too much access, you can have a small system. For limited access, you can do CPTs using a tiny system, just bolted to the floor or something. People have also, changed the CPT system, and these are sea floor CPT systems on the right for pushing full-size cones in deep water as well. Very, very, very interesting technology right there. I want to show you this. I'm not sure if this will work. Oh, it doesn't. I'm sorry. I will share a link later on LinkedIn. So there's a very nice video which I found on YouTube, which actually just shows how the cone pushes down into the ground, but I can't switch it on. So we'll move on. So test equipment and procedures. I want to talk about CPT advantages. But before we talk about advantages, we should always talk about limitations. One of the larger limitations, of course. So one limitation for today in India is that CPT technology requires fairly high capital investment. A large reason for this is because the pushers and the cones and the equipment are not manufactured in India. So everything has to be imported from Europe and North America. You pay customs. So there is a fairly high capital investment. And I think this is something which has possibly discouraged, the rise of in-situ testing in our country so far. But I think things are changing now. It also requires skilled operations. But possibly the largest limitation of CPT is that it works in soil. It does not work in hard strata such as gravel and cemented layers or rock or boulders. Obviously, because it's a push system, it's a push test. So if you have a rock or if you have boulders, the cone will simply go and hit the rock and will stop. It can't push beyond the rock. Of course, people have had success pushing cones in gravel, even in some kind of weak rocks internationally, but you require higher pusher capacities, maybe 20 to 30, 35 ton pusher capacity for that. But largely, I think the main use case for CPTs, you should say, would be in soil. So very good in India, not a problem, because if you look at the northern Indo-Gangetic plain, if you look at the coastal India, so on and so forth, I think CPT is very useful in these kind of geologies. And lastly, I think I don't know it's a limitation, but one one deterrent for CPT right now is that there is still hesitation in technology adoption, and it might take some time for our geotech designers to get used to seeing CPTs in their soil reports and getting used to the numbers and using those numbers in geotechnical design. That said, you look at the advantages, and I honestly feel that the advantages of CPT far outweigh the disadvantages. I always say cheaper, faster, better, right? So it's fast, and we'll see this. So the CPT, the push rate is 2 centimeter per second. So that means you can actually do a 30-meter CPT test or sounding in just 30 minutes or half an hour. Typically, you can do with setup time, etc. You can do about 3 to 4 CPTs per day. The second advantage is it's highly granular, so you get continuous or near continuous data, which is different from, say, boreholes, where you get data points every 1.5 or 3 meters. Here you get almost near continuous data every 2 centimeters. It's very accurate. It's highly versatile. You can go up to large depths. We are pushing routinely up to 40, 50 meter depth in most sites these days. Highly reliable, because it is completely independent of the type of equipment, of the company, of the operator, of the engineer, so on and so forth. It's beautiful, right? Because it's completely digital. So you don't have any kind of human errors. You don't have any kind of other errors the way you have in conventional geotechnics. And you get the same result each and every time, highly repeatable. And it's very modular. We'll see some of this as well. Safe, it's clean, and now this is the tricky part. It's also cost effective. So the cost of CPTs, at least the way we are nowadays, we are retailing CPTs at roughly the same as the cost of conventional boreholes. So I think the largest hesitation was cost in adopting CPTs, and we are trying to eliminate that, because now we are doing CPTs at roughly the same as cost of boreholes. We look at time, right? So I said it's fast, but let's look at how fast. So if you have, say, on your site, if you have to do one borehole to 30-meter depth, typically you'll take 4 to 8 hours in getting the rig to the locations, shifting, setting up the tripod. You need 2 to 3 days for drilling and sampling and testing. Couple of days for sample transport. 7 to 10 days easy for the lab testing. It should not be less than this. And then manually, taking the field and lab test data, compiling it, and coming up with the analysis. So 15 days minimum, 30 days tops is the time that it takes from the time that you start doing a borehole to the time you get the final outcome or the final results. Right? And keep in mind that this is a very difficult and it's a very laborious work involving a lot of men, a lot of people through the entire life cycle of boreholes. Compare that on the right with the CPT. So typically typically you bring your rig to site, you are set up in 1 or 2 hours. You can do a 30-meter sounding, as we said earlier, in 30 to 40 minutes. There is no sample transport, there is no lab testing, and the data is simply transferred to the computer. Click a button and you get your report in 4 to 5 hours. So that's incredible, right? Now, if you scale this to, say, a highway project or any other project where you have 100 boreholes, so you are looking at 6 to 8 months time for investigation using regular drilling rigs versus 40 to 50 days using CPT rigs. And obviously you can optimize the time even further by using multiple teams or multiple rigs. So incredible scale effect in terms of time. At the same time, we also achieve much more accuracy. So this is a typical CPT data. You look at the continuous profiling, and once you get used to this, it becomes very hard to go back to borehole data, because now you have continuous profiling. You get the tip resistance, sleeve friction, and your dynamic pore pressure values, and you're able to catch. When you do CPT, you'll be able to catch even thin layers, as thin as 0.6 mm or 6 centimeters or 7 centimeters. You are able to catch that in your data. Something which would, in conventional borehole drilling would be easily missed. I spoke about repeatability before, and when we saw this graph by Professor Robertson in his book, that he did 2 CPTs together and he put the results on top of each other, and he claimed that the test repeatability is 0.1% of full-scale output. We didn't believe it. So When we got our CPT equipment a couple of years back, we went and we did a lot of tests at the same location. So we used to test, we used to shift it by a couple of feet and test again, and we used to superimpose the data, and we were amazed to find that truly the repeatability of CPT is actually quite fantastic, and you get exactly the same results at the same location. Now, this is very powerful because if most of us, who've been used to, myself included, who are used to dealing with SPT, are used to, accepting the fact that, there is a lot of intrinsic variability in the SPT values. So we were used to seeing a spectrum, 20 to 30% spectrum of SPT values, even at the same location, depending on, who's the operator and how the test was done, which company did the test. And we used to always pick, our design values on the lower end of the spectrum, knowing full well that these are just, errors in the reliability of the test itself. But in the CPT, if you know that you have good repeatability, you can actually, pick your values exactly as per what you are getting. You don't have to add a factor of ignorance to your values. We talked about versatility. So if you look at the left, normally in a conventional investigation program, you have to do so many tests to get what you want. If you want modulus, you may have to do a pressure meter test. If you're in soft clay, you may have to do a field bend shear test. You do an SPT, you may have to do a cross-hole seismic test to get shear wave velocity and so on and so forth. So what I particularly love about the CPT is that with a single push, say in this case of a piezo cone or a seismic cone, with a single push, you get all of these parameters with a single push. So it works out actually a lot cheaper as compared to doing, multiple tests on the same site. If you want a quick profiling, if you want, an initial phase one kind of investigation, I really feel that CPTs are the way to go, because you can go to a site, you can very quickly, in a couple of days or hours, you can do a bunch of CPTs and you can get a very good idea of the ground profile and the various geotechnical parameters at your site. So, you look here how the results can be used. This is a seismic cone. You can see how this is good for not only soil behavior classification, also for getting your consolidation and permeability values, for getting your strength values, and for getting your consolidation values, and so on and so forth. So the complete array of geoparameters you can get from a single push of the CPT. We talk about depth of penetration. I want to clarify this. There is no way to predict the depth to which a CPT would go at any given location, because the depth to which a CPT can push really depends on what is the ground type. So as you push the cone, you are building up on the friction along the cone sleeve, and you also have the cone tip resistance, and really you are limited by the total system force, which is 20 tons. So you know that your thrust is 20 tons. As soon as your your reaction from the soil along the sleeve and the tip equates 20 tons, you can't push any further. So you are limited by the capacity of your pushing equipment primarily. That said, our experience is in most of alluvium locations in North India, we've done now possibly more than 2,000 tests. So our experience is, at most sites, we are able to push to 30 to 40 meters easy. We only get refusal in areas where you have a very hard strata, say in values of more than 75 to 100 ballpark, or if you get rock, obviously you get refusal. If you go to coastal India, we did a couple of tests in Kochi, we were able to push down to 70, 80 meters, no problem. So it really just depends on the strata. And in a sense, that's fine, because, usually geotechnical engineers are interested in knowing, the characteristics of the ground in the soft portion up to, where the hard formation comes. Verticality. So I mentioned that we have an inclinometer actually inside the cone, which is measuring the cone inclination as we push the cone. Now, this is important for two reasons. Number one, since we are measuring the inclination, we are able to correct the values which we get. So you see on the graph on the right, I'm sorry, I don't have a pointer. If you see the graph on the right, you see how the software will actually correct the values, for verticality. The other reason why measurement of inclination is important is because the operator sitting on the ground, right, he can't see the cone. So if the cone, sometimes the cone will go astray and starts getting inclined, and that's dangerous because you can shear off your cone rods and the cone can be left inside the ground. You don't want that. So having an inclination measurement live is very useful, because in case your inclination increases beyond a couple of degrees, it's usually advisable to stop the test and pull out your cone and do it again, rather than losing your cone and losing your rods. This is a seismic cone setup. We'll talk about this later. We talked about the CPT pushing unit already, and we'll talk about this again. I want to mention that CPT is very useful for ground improvement as well. And this is where it's gaining popularity. So if you have a site where you're doing ground improvement, say dynamic compaction or vibrostone columns, I think CPT is a must, because you can actually do CPTs before and after ground improvement, and you can actually see very quickly and on site, you can actually compare the two results, and you can see whether or not improvement has really happened as per design, and you can see up to what depth the ground improvements actually taking place. So if you have a ground improvement project, a very good application of CPT is ground improvement, is checking the efficacy of ground improvement works. So we've been talking about CPTs. Let's look at a sample CPT report. So we are using a software which has been co-prepared by Professor Peter Robertson himself. So this is what a CPT report looks like. Look here. This is the cone tip resistance, the friction ratio, pore pressure, and the soil behavior type. Now, I want to mention that the soil behavior type, and we'll talk about this next webinar, this is not exactly the same as soil classification. This is based on CPT charts by Professor Robertson, and this really tells you what the soil behavior type is. So does it behave like a sand, or does it behave like a silt or a clay, and so on. All these plots are normalized or can be normalized for different overburden pressures. And this is the great part, right? So in the CPT report, because the CPT results are can be correlated to pretty much all geotechnical parameters, you also get your permeability, your equivalent N60 value profile, your Young's modulus, relative density, friction angle profiles. And I want to show you here, if you look at the SPT N60, right? So we are also, for all the projects which we are doing, where we are doing boreholes alongside CPTs, we also then superimpose the SPT N60 values. The red dots are the actual recorded N60 values, and the black line on the second plot is the interpreted SPT N60 profile. And you see how even the N60 values are predicted so well by using the SPT. It's such a good match. I think this is very reassuring to older geotechnical engineers who are more comfortable with SPT. I think this is a great source of reassurance for all of us that the CPT is telling us the same story as what well-performed SPT investigation would tell. Now note here, I'm saying N60 because the N values have to be corrected for 60% energy transfer ratio. Aside from that, you can also get your constraint modulus, shear strength, unbrained shear strength ratio, OCR profile. You get your shear wave velocity profile. This is not measured. This is through empirical correlation with CPT. You get your state parameters, in-situ stress ratio, soil sensitivity, and your effective friction angle. So that's the basic CPT report. And you can also use the data in the same software. You can export the data and you can do a quick liquefaction analysis. I want to mention that if you look at international literature, you have three approaches typically for liquefaction analysis. You can do it based on SPT, CPT, and shear wave velocity. What we have found is, that the liquefaction analysis or the determination of CRR based on CPT and shear wave velocity is far superior, and that's the internationally adopted procedure as well. I think the CRR calculations based on SPT value are not as robust and should be used with caution. So you do get a liquefaction susceptibility analysis. The advantage also is, since CPT is a continuous test, you actually get you get to know the exact zone in which the soils are prone to liquefaction. and not just an approximate zone. We mentioned the dissipation test earlier, and this is what a dissipation test result looks like. Again, very useful for determination of your consolidation and permeability values in situ. Since we mentioned dissipation test, let's look at this a little bit in detail. The dissipation test is it's very simple. So if you recall, you're in a piezo cone, you're actually measuring the dynamic pore pressures as the cone is pushed. Now remember, this is dynamic pore pressures because as you push the cone into the ground, this is a stress on the ground. So naturally, as is always the case, the pore pressures in the surrounding soils are going to react to the stress, and they will increase, or they will spike up, and that's what you normally measure when you're pushing the cone into the ground. Now, what we can do, and this is fairly obvious, is every now and then when we want, all you have to do is stop the cone. So stop pushing the cone and just relax and watch the dynamic pore pressure values over time, and that's a dissipation test. Simple as that. So it looks something like this. So if you are monitoring the pore pressure, the dynamic pore pressures with time, obviously, typically, your pore pressures it's called dissipate, would reduce or dissipate over time in this kind of a graph. And, if you look at it, it looks very familiar to us. This is exactly what you get in a console test, for example, and the data can be used. Hold on. So this data can be used now to essentially calculate your soil compressibility and your permeability. Pretty much the same way as you would do it for consolidation test. So drain versus undrained penetration, I'm not going to talk about this. I'm going to skip a few slides. We are running out of time. And I'll get to the seismic cone penetration test. Very quick, I think for most of us who are familiar with seismics, you have two kinds of waves. You have the compression waves and shear waves. Compression waves are faster, and the direction of propagation of the wave is the same as direction of propagation of the particles which are transmitting the waves. Shear waves are slightly slower, so the shear wave train will follow the compression wave train. But the characteristic of shear wave train is that the direction of propagation of the wave is perpendicular to the movement of the soil particles. So let's see how we use this. Shear wave velocity, why it's important is because it's a fundamental property of any solid in civil engineering, right? And that's what makes it really important. It also connects to the small strain shear modulus, or Gmax, through a simple equation, which is Gmax is rho Vs square. And this is very useful. I think shear wave velocity profiles have been used all through for ground response analysis, for site classification, for hazard analysis. It's very popular. I think there is some conversation that one of the new Indian codes will also require you to do seismic testing at every site to determine the site class. So this is what UBC and 𝐵 used to recommend, is site class A, B, C, D, E, F. And I think there is talk about this coming into the Indian codes as well, which means we will see a lot more seismic testing in the years to come. There are various ways of determining shear wave velocity. So you can obviously, the simplest is you can take samples and you can do lab testing. So you can do a combination of resonant column test and cyclic simple shear, cyclic stress. I forget. You can do this. You can use Bender elements as well in the lab. But this is very painful and it's very expensive and very time consuming. Typically what people do is we do site field testing for seismics. So we can do downhole seismic test or a crosshole seismic test. Now, crosshole seismic test is great. We have been doing it for the last 20-25 years. The only issue is, while it's very, very accurate, a crosshole seismic test, possibly the only downside is the cost and the time which it takes, because you have the time and cost of drilling 2 or 3 boreholes, grouting them, casing them, waiting, and then doing the testing. So it is an expensive test. The seismic cone which we are talking about now is possibly, in terms of accuracy, not as accurate as a crosshole seismic test, but it's a lot faster and it's a lot cheaper. And if you have uniform formation, then it gives you a fairly good profile of average shear velocity, or VS30 profile. What does the seismic test look like? It's fairly straightforward, actually. It's the same cone, except you have a couple of geophones embedded in the cone at the top. So when you are pushing the cone, all you do is, you here. So when you push the cone down, all you do is you stop the cone every now and then, typically every half meter or 1 meters. You stop the cone, and then you have a plank at the ground level, which you can impact on the left and on the right, generating hence when you impact the plank, obviously you generate the seismic waves. These waves are captured in the geophones, which are embedded in the cone or on top of the cone, and the compression and shear wave velocity is calculated by a simple distance over time formula. So that's it. This is very, very efficient. It's accurate and very economical as compared to crossover seismic test. So you look at this setup. It's very simple. I'm going to show you a photo at this site. Oh, here. So this is our seismic cone, by the way. So you'll see. I'm sorry, I don't have a pointer, so you'll have to kind of visualize this. You have the cone at the bottom, and if you see on top where the guy on the right is holding the cone, so that's a seismic module where the geophones are embedded. So we did this very recently, the seismic cone. This is, in fact, as early as last week. We were doing a seismic CPT at a site in NCR. The interesting thing is, and I want to say this, I think the seismic cone gives, because there is no borehole preparation required, there is no grouting and grout setting required, the seismic CPT gives us very, very clean data as compared to borehole methods. More on this in times to come, but this is our first observation. Seismic interpretation is fairly straightforward. It's the same as a downhole seismic test. So you can do a pseudo interval test or a true interval interpretation. Either way, it doesn't matter. And this is what the results look like. So now you get a cone tip resistance, leaf friction, pore water pressure, and the shear wave velocity profile in the same push. I love this because there is no issue with lateral variation. You are getting all your geotechnical parameters at the same location. So you get a lot of confidence in the cross correlations between various geotechnical parameters. Lots of applications of shear wave velocity, of course. If you look at applications of shear wave velocity, it's very common to use input shear wave velocities in earthquake engineering. For example, when we do a shake analysis or a 1D site response analysis, shear wave velocity, as we mentioned earlier, is useful for liquefaction evaluation. You can use the numbers to calculate your dynamic coefficients for design of machine foundations, for deep foundation design, and also for soil identification. I want to say this because, remember, and we'll talk more about this, why is seismic CPT required for soil identification? Because in a seismic test, when you are measuring shear wave velocities, this is a low strain measurement. So you actually are able to capture the effect of aging and cementation, which is otherwise lost in a destructive kind of a test. So if you have, say, cemented or aged soils, and you're doing SPTs or even CPTs in that soil, you will get essentially a lower shear strength profile as compared to what you can interpret from your low strain kind of tests, because you are not in a low strain test like a seismic CPT, you are not breaking the bonds of the soil and you're testing the soil as it is. Anyway, so that's the advantages or the applications of shear wave velocity. Compression wave velocities are also fairly useful. One application of the measurement of compression wave velocity is simply knowing what is the soil saturation or what is the depth of groundwater, simply speaking. You get your Poisson's ratio determination, and you can also use the compression wave profile for determining or detecting unsaturated zones. All in all, I think the VP applications are not as common as the applications for shear wave velocity in most geotechnical applications. We look at soil sampling. We looked at this before. I just want to talk about here. So that's what the soil sampler looks like. It's fairly straightforward. So you have a dummy cone at the bottom, and then you have an area where it's kind of like a syringe. You kind of push the entire assembly into the ground up to the depth where you want to pick up the sample. And then there is a system where you kind of retract the cone like a syringe. You retract the cone in, and the soil actually will go into the cylinder, and the entire assembly can be lifted up, and you get your soil samples for testing. So not much to say about this. It's similar to a piston sampler, except we don't need a borehole now. We can actually use our CPT equipment for collecting these samples. Very useful in case you don't have a drilling machine at site. You just have a CPT pusher at site. You can actually do your CPTs, and if you still need samples, say for chemical testing or for confirmation or for index testing, for confirming the soil type, you can actually swing your CPT at the next location, and you can stoop down, pick up a couple of samples, bring them back to the lab. So very nifty arrangement, and something which is very useful, I think, especially at sites where you don't have boreholes. So that's CPT for you. I had prepared a few slides on the future of CPT for those who are interested. I won't spend much time on this. We've already gone over an hour, but I think if you look at the West, they are coming up with already better pushing equipment. So they've gone up to 35-40 ton capacity pushing equipment. They also have drill rig conversion kits if you look online. So you can actually convert your drill rig into a makeshift CPT pusher through an attachment. Obviously, improvements in cone design, improvements in the software, in the interpretation, so on and so forth. And lastly, you can add, this is also a strength of the CPT, is you can add a lot of sensors, or it's very modular. So you can add a lot of sensors to the arrangement as you wish. And this is what people have added. You'll be amazed at the kind of stuff which people have added. So temperature sensors, geophones, in seismic cone, right? You can have a cone pressure meter. People have even put a camera on the CPT. So when you're pushing the cone, you can actually record an entire video of the soil passing by the cone, and you can visually see the soil as the cone is pushed down. Radioisotopes, dielectric, pH, so on and so forth. So lots of sensors can be added, and this is very useful not only for geotechnical but also for geo-environmental applications of the test. So I want to end here. In any case, my presentation is not moving forward. So I would like to end. Pooja, I think we should conclude. I thank everyone for attending this. We'll take questions. Thank you.
Thank you, sir, for your insightful presentation. Now let's move on to the QA session. Please continue posting your questions in the comment section, and we'll address them one by one. So our first question is from Pratibha Bagaria, and he's saying that how could we correct total cone resistance if we have three pore pressure measurement?
Pratibha, I don't think I understand your question. How can we correct total cone resistance if we have three pore pressure measurement? We don't have three pore pressure measurements, Pratibha. We have one pore pressure measurement, which is, you measure the dynamic pore pressures through a sensor just behind the cone exactly. So, and that pore pressure, that U2 value is actually typically what's called. That's used to correct your cone tip resistance as well as your friction resistance. Maybe message me directly so I can understand the question better. Thank you.
Second question is from Chetan Khandelwal. Does CPT provide good results in rock?
No, Chetan. CPT people have pushed CPTs in very weak or fractured or fragile rock, or soft rock. But typically, you cannot do CPTs in rock, and that's one of the limitations of the test method. So if you have a site where you are expecting rock at shallow depths, my advice to you is don't bother going with CPTs. You can't push a CPT in rock. Rather, I think you'll have to go back to conventional borehole drilling and we can talk more about that as well. If you have fractured rock or fragile rock, our suggestion is always to go triple tube core barrel drilling, so you get maximum core recoveries. But CPT is not applicable for rock. We should be clear.
Next question is again from Chetan Khandelwal. He is asking, can we get instant results on field about soil rock parameters, or we have to analyze data in software only?
That's a very good question, Chetan. We at site, when you're in the acquisition mode, you are able to see the depth, inclination, the cone tip resistance, the friction ratio values, and you're able to see your dynamic pore pressures. But if you want to see the interpreted geotechnical parameters, including profile and gamma, C, phi, so on and so forth, that is something you have to do back in the office, or once the test is completed, because you have to actually import the CPT file in the interpretation software, so that you can't see that website. It's a good question. Thank you.
Thank you for giving the answer, Prateek. Next question is from Vishal. Why N refusal as values 150? I have seen a slide in a slide you mentioned. N refusal as. Sorry.
Got it. Vishal, I'm not sure which slide you're referring to. So N refusal as values 150. I'm not sure. See, the interpretation of refusal. When we say refusal, this is a very broad brush kind of term, right? And people interpret it differently. Some people say refusal means that you can't drill or you can't push further. That is refusal. Sometimes we also give, and every spec is different. Sometimes we define refusal in terms of SPT N values, typically in our contracts. So somebody defines it as N value of 100, somebody defines it at 50, somebody defines it 75. It's up to us how you define it. There is no set definition of refusal. I hope I clarified that, Vishal.
Question is from Hitesh Desai. How to predict a water table?
Good question, Mr. Desai. Water table is, and this is also a good thing. See, since in a piezo cone, since we are measuring the dynamic pore pressures. So now what happens is, and I did not, to be fair, I didn't explain this, is when you are measuring dynamic pore pressures, really now what you get is, so when you're pushing the cone, if you're pushing in clay, right? Clay is, because of its low permeability and low, because low permeability, when you push a cone in clay, your dynamic pore pressures will spike up, right? Because of the effect of the cone. Now what happens is, since clay permeability is very low, the pore pressures don't have time to dissipate back to the hydrostatic line, and in that time the cone has already moved forward. Compare this with a case where you are pushing the cone in sand. So in a free draining sand, when you push a cone in sand, your pore pressure values spike up, but they quickly come back down to the hydrostatic line even before the cone goes to the next step. So if you look at, I should have actually taken out one of the typical. Can you permit me? Let me pull this. Hold on. It's hard to explain. Share screen. Sorry. Let me pull up a typical CPT profile somewhere, and I might be able to here. Perfect. If you can, Pooja, confirm if you can see my screen.
Yeah, yes, sir.
Okay, great. So you look at this. Look at the third plot, which is the pore pressure. Sir, you in your clean sand layer, your dynamic pore pressure line will actually follow your hydrostatic line, right, in clean sands. Whereas in clay, it would not. It would normally be higher than your hydrostatic line. So this is useful because if when you get this, you can actually back calculate in the software. You can back analyze, so using the data in sands, you can back analyze this and you can get your depth of water table in the software itself. The other way is you can actually stop the cone, do a dissipation test. And when you do a dissipation test and in depth, you can actually get your hydrostatic pore pressure at that depth. So once you get that, you can divide by 9.81 and you can get the depth of groundwater. We have found this is fairly accurate actually. The groundwater depth also measurement is fairly accurate from CPTs.
Thank you, sir. The next question is from Akshat Rajput.
Mhm.
He's asking the job opportunities of fresher in this field.
If you love your job and if you are very keen, Akshat, there are always job opportunities in this field. We like to encourage a lot of freshers. We hire a lot of freshers as well. And I think if you truly love geotechnical engineering, you can have a great career ahead. No doubt.
Again, he's asking how affordable is this CPT and in what situation can we prefer that over other conventional testings?
Yes. So very good question. In terms of affordability, uh, so obviously there's a challenge, as I mentioned, the equipment itself. There's some capital investment involved. So the initial investment required for CPT is fairly high, not only in acquiring the equipment, importing it, but also in also in maintaining it, in calibrating it, so on and so forth. That said, because the CPT is very quick and the running expense is not as much, so the costing of CPT in terms of cost to customer is similar as compared to the cost of boreholes. So in terms of affordability for the customer, it is very affordable. It's actually a cheap test in that respect in terms of what you get. And in what situation can we prefer CPT over conventional testing? See, really you have to design this. So I think if your site, if you have rock, CPT is not a good solution. You have to go with other test methods such as boreholes. If you are anticipating soil and soft soils primarily, then I think CPT is a very good option and should be explored.
Thank you for answering, Ravi sir.
Thank
Our
you.
next question is from Vishal again. He's asking, can you recommend a book which we can read all these, or will you share? We'll share the recording with you.
We will share the recording with you, Vishal. And also, in terms of books, I would recommend there is what we call the CPT Bible. You can just Google. So there are three people: so Professor Peter Robertson, Professor Main, and Professor Lunn. You Google their names, and you will come up with their CPT publications. So Professor Robertson, in particular, I really like his book. It's just called Cone Penetration Testing. And I think if you just Google it, there is a free edition which is available online. Pooja, if you remind me, we'll actually post that reference on our LinkedIn page as well. So Vishal, you can download it from our page as well.
Sure, sir. Next question is from Himanshu Joshi. How do results of CPT compare to traditional borehole drilling and the standard penetration test in terms of reliability and accuracy?
Compares very, very well actually. And I think the next webinar, Himanshu, I encourage you to join. In the next part of this webinar, we will be talking about the interpretation of CPT. And in that, we will actually be taking a lot of case studies we'll be presenting where we will be comparing the results of CPT with the results of conventional boreholes at the same project site. So I encourage you to join us next time. And I think we'll spend a full hour answering your question and trying to answer your question. But in short, yes, it compares very well.
There's some thought of Arun Kumar. He's saying that as per my understanding, CPT is to be done only when we are sure with the stratigraphy prior. So I feel this is a secondary test for better understanding soil parameters. What's your opinion on it?
Mr. Arun, I beg to differ. It's the other way around. So typically the thought process is where you have to know your expected geology at least to the extent that you should make sure that you don't have rock at shallow depth. Because if you have rock at very shallow depths, then maybe CPT is not the way to go. That said, if you're not expecting that, then on rather I would say it's the other way around. I would rather do CPTs. Say if you're doing a multiple stage investigation, you're doing a preliminary investigation. It could be pre-bid, pre-purchase, preliminary, whatever. If you're doing the first cut investigation very quickly, I would like to go with CPTs because you can actually go ahead and you can do a bunch of CPTs very quickly and you can get a very quick ground profiling at your across your site. and then you can design your detailed investigation based on those results. So I think I like CPTs as a phase one choice of investigation too.
Next question is from Gaurav Sharma. In what types of soil conditions is CPT most effective, and are there any limitations where other methods should be preferred?
I think except for rock, if you have not soil, any kind of soil, I think CPT is very effective, and uh, it's definitely very useful. There is no other limitation in terms of ground type.
Question from Ankit. How does CPT data influence the foundation design of high-rise structures or heavy infrastructure projects? Can you share any case studies?
That's a good question, Ankit. We will share this again. I'm sorry, but the next part of this presentation, part two, we will be talking about CPT interpretations, as well as we will be looking at how you can calculate SBC based on CPT data. But to answer the question in short, how does CPT data influence the foundation design? It doesn't influence. It's just another data, right? You just get more data for your foundation analysis. So the formulas, the empirical correlations were always there with us. So we always had, correlations between, say, pile capacity and not only N values and C5 values, but also based on CPT data. We always have these correlations. We just never had the input data to plug it in. So if you have the data, you can actually do your analysis based on various methods, and then you can make a judgment call as to what should be your final SBC values. We will share some case studies next time, I promise.
Next question is from Neha Pawar. For projects involving liquefaction risk, how can CPT be used to assess susceptibility, and what precautions should be taken based on the results?
Neha, for projects involving liquefaction risk, I'm actually a huge fan of doing CPTs because, as I mentioned earlier, and if you look at international literature as well, CPT is the preferred method for getting your CRR profile or for getting your factor of safety against liquefaction profile. So CPT is a preferred method. Along with that, I would always like to do a shear wave velocity profiling and possibly a few SPTs with SPT ETR correction. And there are no precautions to be taken for the results. You can get your CPT data and you can plug it into the formulations given in NCR summary report, and you have your CRR profile, which you have a fairly good CRR profile for your site.
Question is from Manali Bhadoria. What are the major differences between using CPT for shallow foundations versus deep foundations like piles?
There's no difference. So CPT is an investigation tool. You should do it. I'm not sure what is the import of your question, but you can use CPT data both for design of shallow foundations as well as for design of deep foundations like piles. It's applicable to both possibly. But if you really want me to split hair, I think I would say that CPT data uh, is even more applicable for determination of pile capacities. And the reason for that is, if you look at the CPT test or the way the CPT is done, it kind of looks like a driven pile. So because the test is actually mimicking the foundation installation, so CPT data historically has been very, very popular for determination of pile capacities in situ, and especially offshore where you don't have time to do boreholes and lab testing. So people have been using for years and years. People have been using CPTs for a quick determination of, fairly accurate pile capacities for the offshore industry. But it's equally applicable to both.
Next question is from Akshat Rana again. In terms of equipment and cost, how does CPT compare to other in-situ testings methods for a large-scale projects like wind farms or solar power plants?
Well, the equipment is more expensive than drilling equipment, definitely, at least today. But in terms of when you say cost, so if you say cost of the test, as I said earlier, the cost of a CPT is works out to be more or less the same as the cost of a borehole for most sites. Again, it will vary depending on quantities and so on and so forth. But typically, the cost of CPTs is the same as the cost of a borehole, but you get it for a fraction of the time, and you get much. We remember we said cheaper, faster, better. So cheaper, faster, better.
And we are taking the last question of today. It
Yes,
is from
please.
Nadil. For using CPT to assess the improvement, post-ground improvement, how do we ensure that the CPT location does not coincide with, say, a stone column location? Because in that case, we will get a refusal.
Yeah, Nadeem, great question. So obviously, if you're doing CPTs in between stone columns, there's always an off chance that you might encounter a refusal because of the gravel. That said, why it's not very common and why I would expect that 90% of your CPTs will go through is, number one, you can actually, obviously you'll do your CPTs in between the columns, right? And typically there is a 2 to 3D spacing between the columns, so there's enough space. And second, when you're doing CPTs, typically you'll meet refusal when you have too much inclination. But when you're doing piezo cone testing, you are actually measuring the inclination and controlling the cone inclination, and you make sure the inclination is not more than, say, 4 or 5 degrees. So your test is actually fairly vertical, right? And so in our experience, when we have done this also, we have done a fair amount of this testing. I think most CPTs would go through full depth without encountering refusal. So it's a great test for checking efficacy of ground improvement, and doing a before and after CPT between the columns or outside the columns is a very good test, because you not only get the extent of improvement, you also get the extent of improvement vertically with depth. So
Thank you, sir, for answering the question.
yeah.
Thank you, sir, for addressing these questions with such clarity and expertise. Like as we approach to the end of today's webinar, I would like to thank all of the attendees for joining us. Your participation and engagement have made this session truly valuable, and we have found you today's discussion informative and helpful, I think. So if you have any further question or would like to continue the conversation, please feel free to reach out us via mail or connect with us on social media. And I'm also excited to announce our next webinar on 19th October, where we will cover cone penetration test, interpretation, application, and its case studies. So don't miss it. Once again, thank you for attending, and we really look forward to seeing you in our future webinars. Thank you, sir. Thank you so much.
Thank you all. Bye bye.